Hi everybody, thank you all for coming to this talk. My name is Sudarshan, I work for Yelp. Here is a brief background about myself. I have about a decade of experience in information retrieval. I started off working with Z3950 clients and servers. I'm not sure how many people out here have heard of those things. Then I spent some time at Symantec using IR techniques for their data loss prevention group. And for the past year, I've been a search engineer at Yelp. A brief outline of this talk, I will talk about the different search services we have at Yelp, why we moved to this new architecture that we call Federation. Then I will dive into how we do indexing with Federation, followed by how we do searching with Federation. And finally, an interesting problem that we solved while implementing Federation. I put this problem up because it involves some interesting fiddling with probability. So how many of you guys use Yelp? Anybody? Great. So if you do use Yelp, you would have used this particular service that we provide that we call Lucene. Now, Lucene is actually a Java-based service which runs over Lucene. It doesn't have anything to do with the C library called Lucene, which is also an indexing library. Lucene is our business search. This service is responsible for serving more than 4 million queries every day. And the search developers at Yelp spend a lot of their time improving the relevancy of this service, as well as ensuring this service stays up. This service allows people to find businesses at Yelp, and it basically is an index of all the business attributes as well as their review content. So Lucene not only powers the search on our website, it also powers the search that happens when you use the Yelp smartphone applications. So here is an example of search results being retrieved on the smartphone application. The image to the side of it is Yelp's virtual augmented reality app called Monocle. Have any of you guys used it? It's a pretty interesting application which overlays information from Yelp's database or Yelp's search indexes onto a picture that you could have of your immediate surroundings. The other Lucene-based service that we have is called Kathy, and we call her Kathy because she likes to talk a lot, and she is responsible for Yelp's talk search. Now our talk index is a lot smaller than the entire review index that we have for business search. This means that Kathy is a lot faster, as well as her memory footprint is a lot smaller than Lucene. List search. Now this service is one of the two Solr-based services that we have. Many years ago, someone set up a Solr configuration file and set it up so that we could index the different lists that we have at Yelp with that Solr service. And it has been running for the past few years without requiring a lot of effort from the search developers to keep it up. Most of the traffic that this service receives is because whenever someone does a search on the Yelp homepage, we search not only the business search, but we also search through the list search index to show lists that are relevant to that search. Even if you are a very heavy user of Yelp, I'm pretty sure you would not have used this particular search service. This is another Solr-based service which allows us to search within the reviews of a particular business or within the reviews written by a particular user. We find that this service receives more health checks than actual queries from users. This service is an homegrown service. It's actually implemented in Python. It provides spelling corrections, and it builds a try and uses the usual Levenstein distance algorithms to come up with spelling corrections for you. Suggest is another homegrown service that we have developed in Java. It builds a try from the business names as well as the common searches in a particular locality. and it provides the different auto-completion suggestions. We recently moved the business search to architecture that we call as federation, and I will try and provide a motivation of why we had to do this. So the first problem that we ran into was our search was slow. We want to ensure that the median search time is less than 100 milliseconds, and we were not able to do that. We had these couple of observations that hard disk latency is very high. It's on the order of 10 million nanoseconds, while a main memory reference takes only 100 nanoseconds. So the easiest way for us to get a great boost in performance was to load the entire index in RAM. We do this using an open source utility called vmtouch, which in turn uses a system call called as mlock, so that all the data corresponding to your index is pinned into memory. We are basically telling the operating system's virtual memory manager that, hey, grab all the data corresponding to these index files, load your page cache with this data, and never ever evict any of these pages. Before switching over to vmtouch, we were doing something like cat the index to dev/null with the hope that we will have significant amount of the index in the main memory. But oftentimes we would find that some of the pages would not be there and our performance would just dive down. So if there is one thing I would like you guys to remember from this talk is that if you want to have a great performance boost, just try and pin your Lucene indices into memory using vmtouch. This led to another problem. Pretty soon our index was too large to fit in the memory of a single machine. So at that time we had machines with somewhere around 32 gigabytes, and we were running into an index that was too large to fit on a single machine. So the first solution that we came up with, and this was about 2 years ago, was to do what we call as geographical sharding. Now we are going to split the index that we have based on the location of a business. So because Yelp is a local search engine, when someone is searching in San Francisco, the businesses in New York don't really matter. So we can easily split the single index into two indices based on some kind of geographical boundary. Now we had to choose this geographical boundary very carefully because we didn't want to split up any area where we would be getting queries. If we got queries from the boundary of those two shards, then we would have to query both the shards to return the results. So some search engineers spent a lot of time and they figured out that here is this longitude, 116 west, slightly west of Las Vegas. If any of you guys have driven around that area, you would see that you can drive for miles without seeing any sign of population. And they decided that, okay, we'll split the index on this boundary. Now, whenever you search from the west of this particular longitude, you're going to be searching only in the west index. Whenever you search from the east of this longitude, you're only going to be searching the east index. There are some problems with this sharding strategy. Firstly, finding such a boundary is difficult. It's not always easy to find areas which don't have any population. The second problem that we ran into was our index was growing really fast. Pretty soon we realized that the index for only all the businesses in San Francisco would be so large that it would require to be split up. So it's really difficult to split an index like that. Like we can't really split the San Francisco index on the Van Ness corridor or something like that. So we came up with this strategy which we call as federation. So now we are going to split the index across multiple machines. And we are going to split the index based on the different business IDs. And the important thing to notice while doing the split is these business IDs must be mapped to the different machines in a uniform and randomly distributed manner. This uniform distribution ensures that the TF-IDF scores from the different machines are going to be comparable. So how do we do this assignment? Now, a simple way of ensuring that you're going to be randomly assigning businesses to these shards is to first hash the business ID. Once you take a hash of the business ID, you can then mod it with the length of your shard list and basically index your shards with whatever you get as the mod, and that becomes the mapping of the business ID to the shard. However, there is a problem with this strategy. We decided to switch over to federation because we saw our index was growing really fast. That meant that we would always need to keep adding more and more machines. Now, with this strategy, every time you added a new shard, you would have to re-index all your businesses because their mapping would change. So the solution for this was, there's this interesting quote by a guy called Butler Lamson in this book, Beautiful Code. And he basically says that every programming problem can be solved by adding another layer of indirection. And that's the strategy that we used. So out here you will see that we have the hash function, which is going to map the business ID into the number range, say 0 to 2 raised to 32 minus 1. Now we divide that number range into a bunch of virtual buckets. So we divide them into 1024 virtual buckets. And these virtual buckets are mapped to the different shards by a static configuration. So this particular strategy is also pretty commonly used in a lot of NoSQL stores. I think the same strategy is used by Dynamo, React, as well as Memcache. The advantages of this strategy is that we have a lot of flexibility now. Whenever we want to add a new shard, we can basically decide which virtual buckets should be moved to the new shard. Then we need to re-index only businesses that fall in those virtual buckets. Also, if a particular shard has become a hotspot, we can just decide to take away some virtual buckets away from that shard. All this can be done by changing the static configuration, running an indexing job which will re-index the businesses that have been impacted by the change in the static configuration. So that was federation. Now we will talk about how indexing works under federation. So before I dive into indexing, I'll try and give a high-level view of Lucene's architecture. So when I say service, we mean something logical that we are going to query and get back results. A service can have multiple shards. Each of those shards will have a replica, and there will be a search process which is serving results from that replica. So the way we have it set up is that we have a separate set of servers which we call as masters, on which we do indexing, and there is usually one master per shard. Then we have a bunch of servers that we call as slaves, who actually serve out the search queries, and for every replica of a shard, we have a slave. So Luce indexing. We have a process that we call as LuceQ, which monitors the database to see if any of the business attributes that we are indexing have changed. Now, this LuceQ process is going to look at the business, see whether it was a French business or whether it was an English business which belonged to the West shard, and then decide to which set of masters it should be sent for indexing. Once that decision has been made, so for example, you determine that here's a business in San Francisco and it should go to the set of masters corresponding to the West shard, we then have to decide exactly which shard it should go to. And that is done by hashing the business ID, as I had explained, looking at which virtual bucket that hash falls into, then looking at the static configuration to determine which shard that virtual bucket maps onto, and finally sending that business to the master of that particular shard for indexing. We have a cron job that runs every 2 hours and asks these masters to take a snapshot so that we could have a version of the index that's suitable for replication. Once the snapshot is taken, we basically have each slave requesting an rsync of the new index from the master of that shard. So for example, what we see here is that we have shard 1 with 3 slaves, and each of those slaves is serially going to request the index from its master. While the new index is being rsynced to that particular shard, we actually take the shard out of the load balancer. We don't serve any traffic from the particular slave while it is receiving the new index. This is because this new index rsync is an IO intensive operation, and we are afraid that the performance of the search queries will drop while this rsync is happening. So rsyncs happen in serial to different members or different slave members of the same shard. However, we can do this rsync in parallel across different shards. Once this rsync is completed and the slave has the new index, we want to start serving traffic from the new index. So the first thing that we do is we kill the VM touch process. This allows us to kick the old index out of memory. We start the VM touch process again and tell it to load the new index into memory. Once the new index is loaded, we start our service. We run a bunch of warming queries from the log that was already written on that particular slave. This set of warming queries ensures that all the JIT compilation, the correct sizing of the different generations of your Java heap, as well as all the cache warming happens before we start serving any production traffic. Once we are done serving these warming queries, we notify the load balancer and say, hey, this slave is ready, you can start sending traffic to it. So that was the indexing part, and now that we have the new indexes on our slave machines, let's see how searching works over them. So because we have a distributed index, we need a component which will allow us to search all these different machines which have parts of our index in parallel, get all the results from them, and create a coherent result from them and send it to the search servlet, which is actually going to display the results to the user. So the federator is the component that's responsible for that. It's actually Python code that we wrote, which runs within the Python web processes, which are serving the search requests. We use an open source Python library called Tornado, and the IO loop of this library so that we can search all these different charts in parallel. And the transfer protocol used for this is JSON RPC. And the interesting thing about this is all this is around 650 lines of Python code. Now, the individual pieces that are responsible for actually doing the search over the index are what we call as Lucene servers. These are Java processes which are using the Lucene library. Now, we do a lot of interesting things with these Lucene servers. So we handle different queries very differently. For example, if you look at a query like hotels in San Francisco, we want to show you the highest rated hotels in San Francisco. We don't want to show you CD hotels in San Francisco which have hotels as one of the tokens in their name. However, if you are searching for something like Hyatt Regency San Francisco Airport, we want to show you that exact business. So depending on the user's query, we decide if we are going to do a search in the name field, or if we are just going to search the category field. And this allows us to serve different types of queries and provide high relevance for them. Another modification of the query that we need to do out here is we don't just take a query and search all the reviews with that particular query. So for example, if you have a query like restaurant good for kids, we are not going to search the review text with restaurant and good for kids. We are going to convert the good for kids phrase into the business attribute good for kids, and then we are going to show you businesses which have the attribute good for kids. So in addition to these modifications to the user query, the Lucene server is also responsible for gathering the top results of the query, as well as collecting attribute statistics for different attributes such as, say, neighborhoods, features, price. So this faceted navigation structure that you see on the top of the search results is basically built using a custom collector that is going to collect attribute counts for these different attributes. Now, these queries are run against the Lucene library, which is like the most important part of the Lucene server. This library provides us with how relevant a particular business is to a particular query. So if you look at a business like, say, Arizmendi Bakery in San Francisco, which is very popular for its pizzas, you'll find that a lot of reviews of this bakery have the word pizza in them. The document that corresponds to this business is basically a concatenation of all those reviews. This means that the term pizza will be very frequent in that particular document, and Arizmendi Bakery will have a high word score for the query pizza. This ensures that we can show results that are highly relevant for a particular query to the user. We are currently still stuck on Lucene 2.4. We are working to try and upgrade our Lucene code to 2.9. So once the Lucene server returns its results to the federator is responsible for combining those results. So the federator needs to sort those results as well as sum up all the statistics that were gathered by the individual servers. In addition to this, the federator has one more task. Have any of you guys heard of this technique called as successive query relaxation? So successive query relaxation is a technique where suppose you have a multi-term query, say like Harry Potter. You don't want to do a straight up Boolean search for Harry and Potter. The first thing you try to do is you do a phrase search for Harry Potter and see if you can return all the results that a particular user has required. If you can't meet the requirement of returning all the requested results, you then try with an easier query. You say that instead of the phrase query Harry Potter, let's try with a span-year query Harry Potter. Again, if that query doesn't work, you try with a Boolean query Harry Potter. And finally, you just try with an OR query, which is the term Harry or Potter. So we do something similar with the geobonds of search when we are trying to serve results. So out here, if you're searching for, say, coffee in Los Angeles, we are going to be able to show you a lot of relevant coffee shops right in the center of Los Angeles. So we don't have to change the geobonds of search. However, if you're searching for something like snow tubing in Los Angeles, there isn't going to be anything in the center of San Francisco which is going to meet that requirement. So we expand our geobond to include ski resorts which are actually pretty far away from San Francisco. Now, this is something that we have to do at the federator because each individual server is not aware of results from other servers to determine what should be the geobond of search. And again, the interesting thing about this is we had around 1,500 lines of Java code which was doing this on a single server. But we ported most of that logic to Python in our federator, and it turned out to be somewhere around 150 lines of code. So the earlier diagrams that I had shown you about federation were kind of lies. The federator doesn't talk to the different shards directly. It has to go through a load balancer so that we can have different replicas of each shard running, and we can do load balancing as well as high availability between those different replicas. Here is an interesting problem that we came across while trying to implement federation and how we solved it. So what we want to notice is that the number of hits that we need to return to satisfy a particular search is given by whatever is the start that the user has browsed to and the count that the user wants to get from that start location. If the user is requesting, say, with the start as 490 and the count as 10, it means that we have to return 500 results. Now, the naive way of returning 500 results is to ask each shard to return their top 500 results and then sort them. The reason for this is there is a very, very, very low probability that all 500 results can be on a particular shard. So unless you request whatever the user is asking from each shard and then sort, you can't guarantee that you will always be able to return the results in the right order. Okay, so here is an example where I try to show it in more detail. So out here we have, say, around 50 results randomly distributed among 5 different shards. And say we want to get the top 10 results. Now, you don't have to collect 10 results from each of these shards to get the top 10 results. You can observe that out here empirically that if you only get the top 4 results from each shard and then sort them, you could still meet this requirement of returning 10 results. So we model this problem as a probability problem. We say that every hit has a probability of 1 over n of being in one of these n shards. Now, the probability that r of the top k hits are in a particular shard is given by this binomial distribution. Now, say you have 100 hits and you have 5 shards. So on an average, 20 of those hits would be in each of those shards. That's what we have out here with the mean as k into p, where k is 100 and p is 5. P is 1 over 5. The variance for a binomial distribution is given by kp into 1 minus p. So determining the mean is not enough. You also need to know the variance to figure out what kind of distribution you have. Now, the standard deviation is the square root of variance. And finally, we came up with this formula for determining how many results we should pick up from each shard. And that is given by the mean plus 6 times standard deviation. So how do we decide that it's going to be 6 times standard deviation? To do that, we needed to run a bunch of simulations. So out here we have this formula where the first row is average plus a single standard deviation. And say if we have, if you are looking for the top 100 results with 5 shards, this means that we would need to pick up 24 results from each shard. And this will result in a probability of a mistake. By mistake, I mean that we are showing at least one result that is not correctly ordered, or we are missing one of the top 100 results. And the probability of a mistake is still pretty low. If we move it to 3 times standard deviation, the probability falls even lower. And finally, if we move it to like 6 times standard deviation, we have like a 1 in a million chance of something being wrong. And with my Python simulation, I actually never managed to get a reasonable number out there. But there's still a pretty low number out there which says that we could have a wrong result. So I repeated the same simulation using R, and I came up with this graph which shows that if you are grabbing the average plus 6 times standard deviation, your probability of error is very low. So I guess the moral of the story is You can look at the correctness of your system as another attribute that you can trade off, just like you look at the memory of your system or the speed of your system as attributes that you could trade off against. This strategy gave us lots of benefits. We found that we have almost 50% savings when you are trying to get the top 100 results, and we have over 77% savings when you are trying to get the 1,000 results. The number 44 as well as the number 228 are basically given by plugging in the values 100 and p as 0.2 in the formula that I had on one of the previous, in this formula. So what's the future of search at Yelp? We are trying to work on an in-memory index for our Lucene indices, and we also want to move away from the current master-slave architecture that we have and move towards real-time search. The Yelp search team is hiring. If you're interested in any of the work that we are doing, please talk to me. That's all I have. Are there going to be any questions?
So your efficiency trick with figuring out, how many results
right.
you have to grab for the shards.
We don't actually use this probabilistic method of retrieving results till we have more than 30 results that are to be retrieved. The reason for that is there is a cost of doing the network trip to each of your shards. And if you're going to do that network trip, you might as well get a bunch of results. So okay. We don't have to do this probabilistic trick unless you're retrieving more than 30 results.
Hi, so I was curious, when you're doing your sharding, how you determined what the size of your shards should be?
Right, good question. So we decided to split up these shards with a view of having a lot of future growth. So before we split up the shards, our index size was close to 30 GB. We decided to split it up to somewhere around 5 GB. So if we have like 64 gigs machines, we could, even with the exponential rate of growth in our reviews, we could still continue with this architecture for somewhere around 2 to 3 years.